Hello, everyone. Today, we're going to talk about a very basic but useful theorem called the limit of a sum theorem. It's one of the four fundamental limit properties. The concept behind this theorem is quite simple and intuitive. If two functions each have a limit, then the limit of their sum is equal to the sum of their individual limits. Let's look at the mathematical expressions on the slide. First, the initial condition: as x approaches 1, the limit of the function f1 is L1. Next, the second condition: as x approaches 1, the limit of the function f2 is L2. Then, naturally, our conclusion is, as x approaches 1, the limit of the sum of these two functions, f1 plus f2, will be equal to L1 plus L2. Doesn't that sound just like common sense? Now, let's see how to rigorously prove this intuition using a mathematical approach. We'll use the epsilon-delta definition of a limit. First, we know the definition of a limit is, for any epsilon that is arbitrarily small, I can find a delta such that the function's value is very, very close to its limit. So, let's start with the first limit. Because the limit of f1 is L1, it means that as long as x is close enough to 1, the value of f1 will be close to L1. Given any epsilon, since the limit exists, a delta 1 can be found such that the absolute value of x minus 1 is less than delta 1. For our proof, we'll specifically choose this delta 1 to be epsilon over 2. This ensures that the distance between f1's value and L1, that is, the absolute value of f1 of x minus L1, will be less than our chosen epsilon over 2. By the same logic, for the function f2, whose limit is L2, given any epsilon, a delta must exist. We'll use the same epsilon for this discussion. Since the limit is assumed to exist, we can find a delta 2 such that the absolute value of x minus 1 is less than delta 2. Here, we'll choose delta 2 to be epsilon over 4. This guarantees that the distance between f2's value and L2, the absolute value of f2 of x minus L2, will also be less than epsilon over 2. Now, let's add the values of these two functions. We want to see the distance between their combined value and the sum of their limits, L1 plus L2. This distance is the absolute value of f1 of x plus f2 of x, minus the quantity of L1 plus L2. Based on the triangle inequality we've learned, this value will be less than or equal to the absolute value of f1 of x minus L1, plus the absolute value of f2 of x minus L2. As we've just established, both of these terms are less than epsilon over 2, so their sum will certainly be less than epsilon. Therefore, for the given epsilon, we need to be careful to choose a delta that is the minimum of delta 1 and delta 2. This ensures that the absolute value of the total sum is less than epsilon. You see? Based on the definition of a limit, we've successfully proven that as x approaches 1, the limit of f1 of x plus f2 of x is equal to L1 plus L2. Through this rigorous proof, we can confidently use this theorem. That's the beauty of mathematics. I hope today's lecture has given you a deeper understanding of this theorem. Next, I'll give a simple example to show you the thought process behind this proof. Please pay close attention to how to follow the same steps to solve it yourself.